Have you ever wondered why the universe has a speed limit? Why is it that no matter how powerful our rockets become, no matter how advanced our technology gets, we can never push anything faster than light? The answer isn't what you think. It's not because we lack the technology or the energy. It's because the very fabric of reality itself makes faster-than-light travel not just difficult, but fundamentally impossible. And here's the truly mind-bending part. This cosmic speed limit isn't really about light at all. If you're fascinated by these profound truths about the structure of our universe, make sure to subscribe and hit that like button to join us on more mind-expanding journeys through space and time. And here's a question for you. If you could break the speed of light for just 1 second, where in the universe would you go? Let me know in the comments below. I'll choose the most creative answer. Now, let's begin to understand why this cosmic barrier exists and what it reveals about the deepest nature of reality itself. Look up at the night sky and watch the stars twinkling in the darkness. The light from those stars has been traveling through space for years, decades, even centuries to reach your eyes. That light is moving at approximately 186 282 miles per second, and nothing in the universe can go faster. But why? To understand this, we need to go back to 1676, when a Danish astronomer named Ole Rømer made a discovery that would change everything. Rømer was studying Jupiter's moons, carefully tracking when they disappeared behind the planet and when they reappeared. He noticed something strange. The timing of these eclipses seemed to change depending on where Earth was in its orbit. When Earth was closer to Jupiter, the eclipses happened earlier than predicted. When Earth was farther away, they happened later. The only explanation that made sense was revolutionary. Light didn't travel instantaneously. It had a speed, and it took time to cross the distance between Jupiter and Earth. This was the first time in human history that anyone had measured the speed of light with any real precision. For the next 2 centuries, scientists worked to refine this measurement. By the late 1800s, physicists like Albert Michelson had measured light speed to incredible precision using rotating mirrors and carefully measured distances. But these precise measurements created a puzzle that would shake the foundations of physics. According to everything scientists knew about motion, speeds should add up in straightforward ways. If you're on a train moving at 60 miles per hour and you throw a ball forward at 20 miles per hour, someone standing still should see the ball moving at 80 miles per hour. This is just common sense. But light doesn't follow this rule, and this fact would lead to one of the greatest scientific revolutions in history. In 1887, 2 American physicists, Albert Michelson and Edward Morley, conducted an experiment that would inadvertently prove something shocking about the nature of light and the universe itself. They were trying to detect something called the luminiferous ether, a substance that scientists believed filled all of space and carried light waves, much like air carries sound waves. Earth orbits the Sun at about 67,000 miles per hour, so if this ether existed, Earth should be moving through it like a ship moving through water. Michelson and Morley reasoned that light traveling in the same direction as Earth's motion through the ether should move faster than light traveling perpendicular to it, just like a swimmer swimming with a current moves faster than a swimmer crossing it. They built an incredibly sensitive device called an interferometer to detect these tiny differences in light speed. But when they ran their experiment, they found something completely unexpected. Nothing. No difference at all. Light traveled at exactly the same speed in every direction, regardless of how Earth was moving. They repeated the experiment at different times of year when Earth was moving in different directions and got the same result every time. Light speed was constant, period. This result baffled physicists. They invented elaborate theories to explain it, suggesting that objects somehow contracted as they moved through the ether, or that time itself was affected by motion through this mysterious substance. But all these explanations felt artificial, like band-aids on a theory that was fundamentally broken. Then, in 1905, a 26-year-old patent clerk named Albert Einstein published a paper that would change everything. Einstein started with 2 simple assumptions. First, that the laws of physics are the same for all observers moving at constant speeds. And second, that the speed of light in a vacuum is the same for all observers, regardless of their motion. From just these two principles, Einstein derived consequences that seemed to defy common sense but were mathematically undeniable. According to Einstein's special theory of relativity, as objects move faster, time slows down for them relative to stationary observers. Lengths contract in the direction of motion. Mass increases, and most importantly for our question, the energy required to accelerate an object grows exponentially as it approaches light speed, reaching infinity at light speed itself. This isn't a practical limitation that better technology might overcome. It's built into the mathematical structure of space-time. To understand why nothing can exceed light speed, we need to understand what light speed really represents. Here's the key insight that changes everything. Light speed isn't fundamentally about light. It's about the structure of space-time itself. Light travels at this speed because photons have no mass, so nothing slows them down from moving at the universe's natural maximum speed. But this speed, this cosmic speed limit, exists whether light exists or not. It's woven into the fabric of reality. Think of space-time as a four-dimensional landscape where 3 dimensions are space and 1 is time. Everything in the universe is constantly moving through this 4-dimensional space-time at a constant speed. Right now, as you sit reading this, you're moving through time at 1 second per second. You're traveling into the future at a steady rate. But here's the crucial part. Your total speed through space-time is always constant, always equal to the speed of light. When you're sitting still, all of your motion is through time. But when you start moving through space, some of that motion gets diverted. The faster you move through space, the slower you move through time. This is why time dilation happens. It's not some weird side effect of high speeds. It's a fundamental feature of how space-time works. Your total velocity through space-time remains constant, but it gets divided between motion through space and motion through time. This creates a profound symmetry. The speed of light is the conversion factor between space and time. It's not just a speed limit for objects moving through space. It's the fundamental constant that relates spatial distances to temporal durations. Let's examine what happens when you try to accelerate something toward light speed. According to Newton's classical physics, force equals mass times acceleration. Double the force, you double the acceleration. Simple. But Einstein showed that this formula is only approximately true at low speeds. As you approach light speed, something changes. Your mass, or more precisely your inertial mass, increases. This doesn't mean you gain atoms or get physically bigger. Instead, the energy of your motion manifests as increased resistance to further acceleration. At 10% light speed, this effect is barely noticeable, just a 0.5% increase. At 50% light speed, your effective mass has increased by about 15%. At 90% light speed, you're more than twice as massive. At 99% light speed, you're 7 times more massive. And here's where the mathematics becomes absolutely unforgiving. At light speed itself, your mass would become infinite. The Large Hadron Collider at CERN provides us with perfect real-world evidence of this effect. This massive particle accelerator, the most powerful ever built, accelerates protons to 99.9999991% of light speed. That's incredibly close to the cosmic speed limit. These protons zip around the LHC's 17-mile circumference 11,000 times per second. To reach this speed, each proton is given enormous amounts of energy, equivalent to about 7,000 times its rest mass. The LHC uses enough electricity to power a small city. Yet, despite all this energy, despite the most advanced technology humanity has ever created, the LHC cannot push protons to light speed. Every attempt to add more energy doesn't make them go proportionally faster. Instead, the additional energy manifests as increased mass. The protons get heavier and heavier, requiring exponentially more energy for each tiny increment of additional speed. This isn't a technological limitation. The mathematics of relativity are absolutely clear. Reaching light speed would require infinite energy, and the universe simply doesn't contain infinite energy. But let's think about what this really means. According to Einstein's famous equation E equals mc squared, mass and energy are equivalent, related by the speed of light squared. Every bit of mass contains enormous amounts of energy. A single kilogram of matter, if converted entirely to energy, would release 90 quadrillion joules, roughly equivalent to 21 megatons of TNT. This is why nuclear weapons are so powerful. They convert a tiny fraction of mass into energy. But this equation works both ways. Energy also has mass. When you heat up a cup of coffee, it actually becomes slightly more massive due to the added thermal energy. The increase is impossibly tiny, about a trillionth of a gram, but it's real. When the sun fuses hydrogen into helium, the mass of the helium produced is slightly less than the mass of the hydrogen that went into it. The missing mass has been converted to energy, which radiates away as sunlight. This is happening constantly, with the sun losing about 4 million tons of mass every second through this process. This equivalence between mass and energy is why the cosmic speed limit exists. As you accelerate, you're adding energy to an object. But that energy has mass, making the object more massive, which makes it harder to accelerate further. The faster you go, the more energy you need to add. But the more energy you add, the more massive you become, requiring even more energy to accelerate. It's a vicious cycle that spirals toward infinity as you approach light speed. Recent experiments with the relativistic heavy ion collider at Brookhaven National Laboratory have confirmed these effects with stunning precision. When heavy atomic nuclei are accelerated to near light speed and collided, they behave exactly as relativity predicts. Their increased relativistic mass affects how they interact, how they fragment, and how they produce new particles. Every measurement confirms Einstein's century-old predictions to incredible accuracy. But here's where things get really interesting. This cosmic speed limit isn't just about matter and energy. It's about information itself. No signal, no message, no influence of any kind can propagate faster than light. This creates what physicists call light cones, regions of spacetime that can causally affect each other. Your future light cone contains all the events you could possibly influence. Your past light cone contains all the events that could have influenced you. Events outside these cones are in what's called elsewhere, regions of spacetime that cannot interact with you without exceeding light speed. This structure has profound implications for causality, for the relationship between cause and effect. If faster-than-light travel were possible, it would allow for time travel into the past with all its attendant paradoxes. Let me explain why faster-than-light travel necessarily implies backward time travel. This is one of the most subtle and profound implications of relativity, and it's absolutely crucial for understanding why the cosmic speed limit must exist. Imagine you have a friend on Mars about 12 light-minutes away. You send them an instantaneous faster-than-light message. From your perspective on Earth, the message arrives at Mars at the exact same moment you sent it. But here's the thing. Simultaneity, the concept of events happening at the same time, is relative. It depends on your frame of reference. From the perspective of someone moving at high speed relative to you and Mars, your instantaneous message didn't arrive simultaneously with its sending. Due to the relativity of simultaneity, moving observers see time differently. To them, your message might arrive before you sent it. Now, if your friend on Mars could send an instantaneous reply, and if they're moving in the right reference frame, their reply could arrive back on Earth before you sent your original message. You would receive a response to a question you haven't asked yet. This isn't just a theoretical curiosity. It would allow you to send information into your own past, creating the possibility of paradoxes where effects precede their causes. The grandfather paradox illustrates why this is problematic. If you could send information to your past self telling you not to send the original message, what happens? Do you send it or don't you? If you don't send it, then you never receive the message telling you not to send it. So you do send it. But if you do send it, you receive the message and don't send it. It's a logical contradiction, a situation where the universe would have to be in two mutually exclusive states simultaneously. The mathematics of special relativity shows that any form of faster-than-light travel or communication creates the potential for such causal loops. The only way to preserve causality, to maintain the logical consistency of cause and effect, is for the cosmic speed limit to be absolute and unbreakable. Recent work in quantum information theory has strengthened this conclusion. Researchers at institutions like the Perimeter Institute for Theoretical Physics have shown that faster-than-light information transfer would violate fundamental principles of quantum mechanics, creating situations where quantum systems could be in impossible states. Now, you might be wondering about quantum entanglement. You've probably heard that when two particles are entangled, measuring one instantly affects the other, no matter how far apart they are. Einstein called this spooky action at a distance and was deeply troubled by it. Doesn't this violate the cosmic speed limit? The answer is subtle but important. No, it doesn't. Quantum entanglement is real. When you measure an entangled particle and find it in a particular state, its partner instantly goes into a corresponding state, even if it's on the other side of the galaxy. Experiments have confirmed this correlation to incredible precision. But here's the crucial point. You can't use entanglement to send information faster than light. The results of quantum measurements are random. You can't control what result you'll get when you measure an entangled particle. Only when you compare the results of measurements on both particles, using normal, slower-than-light communication, do you see the correlation. It's like having two coins that always land on opposite sides, no matter how far apart you flip them. The correlation is real and instantaneous, but you can't use it to send a message. You can't control which side your coin lands on, so you can't encode information in it. The precise mathematical framework for this comes from quantum field theory, developed over decades by physicists like Richard Feynman, Julian Schwinger, and Shinichiro Tomonaga. In quantum field theory, particles are understood as excitations in quantum fields that fill all of space. These fields can only propagate at or below light speed. Virtual particles, temporary fluctuations in quantum fields, can briefly violate energy conservation due to Heisenberg's uncertainty principle, but they can never carry information faster than light over any measurable distance. The structure of quantum field theory enforces the cosmic speed limit at the deepest level of reality. Faster-than-light particles or influences would require exotic properties that appear to be forbidden by the mathematical consistency of the theory itself. But what about the expansion of space? We know that distant galaxies are moving away from us, and the farther away they are, the faster they're receding. In fact, galaxies more than about 14 billion light-years away are receding faster than light. Doesn't this violate the cosmic speed limit? Again, the answer reveals something profound about what the speed limit really means. The galaxies aren't moving through space faster than light. Space itself is expanding between us and them. It's like dots drawn on a balloon. When you inflate the balloon, the dots move apart, not because they're moving across the balloon's surface, but because the surface itself is stretching. The cosmic speed limit applies to motion through space, not to the expansion of space itself. General relativity, Einstein's theory of gravity and space-time, allows space to expand or contract at any rate. This expansion doesn't carry information or allow for causal influences to propagate faster than light, so it doesn't violate the fundamental principle that effects cannot exceed their causes. The Hubble Space Telescope, and more recently the James Webb Space Telescope, have observed galaxies so distant that their light has been traveling for over 13 billion years to reach us. Due to the expansion of space during that time, those galaxies are now over 30 billion light-years away and receding at several times the speed of light. This is completely consistent with relativity. What we can never do is travel through space to reach them faster than light. In fact, most of these distant galaxies are already beyond what's called a cosmic event horizon. Their current light will never reach us because space is expanding too fast. They're not just far away, they're fundamentally unreachable. This creates a kind of cosmic isolation. In the far future, as dark energy continues to accelerate the universe's expansion, our local group of galaxies will become increasingly isolated. Other galaxy clusters will disappear beyond the cosmic horizon. redshifted to infinity. Future civilizations will live in a universe that appears to contain only their local galaxies, surrounded by darkness. So we've established that the cosmic speed limit is real and unbreakable for anything moving through space. But what about the creative solutions proposed by science fiction? What about warp drives and wormholes? Could these offer a way around the light speed barrier? The Alcubierre drive, proposed by Mexican physicist Miguel Alcubierre in 1994, is probably the most famous of these concepts. It's based on a real solution to Einstein's field equations from general relativity. The idea is elegant. Instead of moving faster than light through space, you warp space itself. You contract space in front of your ship and expand it behind, creating a warp bubble that carries you along. From your perspective inside the bubble, you never exceed light speed locally. Space is doing all the work. The mathematics shows this is theoretically possible within general relativity. NASA's Advanced Propulsion Physics Laboratory, informally known as EagleWorks, even conducted experiments to see if tiny warp bubbles could be created in laboratory conditions. But here's where physics throws up insurmountable obstacles. First, the Alcubierre drive requires something called exotic matter. Matter with negative energy density. This is not antimatter, which has positive energy. Negative energy density means less than the energy of empty vacuum, which is already as low as you can normally go. The Casimir effect demonstrates that negative energy densities can exist in tiny amounts between closely spaced metal plates, but scaling this up to useful quantities appears to be impossible. The amounts needed are staggering. Early calculations suggested you'd need the mass-energy equivalent of the entire observable universe worth of exotic matter. Refined calculations by Harold White at NASA reduced this to merely the mass of Jupiter, but that's still impossible by any reasonable standard. And it's not just exotic matter you'd need. You'd need to be able to manipulate it precisely, creating a bubble around your ship while somehow remaining causally connected to the bubble's boundary so you could steer it. Recent work by physicists like Sabine Hossenfelder has shown that this creates additional problems. If you're inside the warp bubble, you're causally disconnected from its leading edge. You can't send signals to the front of the bubble faster than light, which means you can't control where it's going. You'd be trapped inside, unable to steer, unable to stop. Moreover, physicist Stephen Hawking proposed something called the chronology protection conjecture. The idea that the laws of physics somehow prevent the creation of closed time-like curves, paths through space-time that loop back on themselves, allowing time travel to the past. Any method of faster-than-light travel, including warp drives, could potentially be used to create such paradoxical situations. The universe seems to have built-in safeguards against this. Every proposed method of exceeding the cosmic speed limit runs into similar problems. Wormholes, shortcuts through space-time predicted by general relativity, would also require exotic matter to keep them open. Even if we could create a wormhole, it couldn't be used for faster-than-light travel in a way that preserves causality. Traversable wormholes appear to be fundamentally impossible, or at least require conditions so extreme and exotic that they might as well be magic. Some physicists have proposed that particles called tachyons, hypothetical particles that always travel faster than light, might exist. The mathematics of special relativity actually allows for such particles. But tachyons would have imaginary mass, in the mathematical sense of involving the square root of negative numbers. They would violate causality, allowing effects to precede causes. And most problematically, their existence would make the quantum vacuum unstable, causing it to decay and fill with tachyons spontaneously. Decades of experiments searching for tachyons in cosmic rays, particle accelerators, and astronomical observations have found nothing. The universe appears to contain no faster-than-light particles. This absence seems to be another consequence of maintaining causal structure. The speed of light isn't just the fastest speed allowed. It appears to be the only speed at which causality can work consistently. String theory, one of the leading candidates for a theory of quantum gravity, provides additional insights. In string theory, the fundamental objects aren't point particles but tiny vibrating strings. Different vibration patterns correspond to different particles. The speed of light emerges from the properties of these strings and the geometry of spacetime. Some versions of string theory suggest additional spatial dimensions beyond the three we experience, but these extra dimensions are compactified, rolled up so tightly that they don't affect everyday physics. Even with extra dimensions, the fundamental speed limit remains. Motion through the extra dimensions doesn't provide a shortcut around it. Loop quantum gravity. Another approach to quantum gravity developed by physicists like Carlo Rovelli and Lee Smolin suggests that spacetime itself might be quantized, made of discrete chunks at the tiniest scales, around the Planck length of 10 to the minus 35 meters. At this scale, space and time become fundamentally granular, like pixels on a screen. Even in this picture, the speed of light emerges as a fundamental property of how these quantum bits of spacetime connect and interact. The cosmic speed limit appears to be built into the structure of reality at the deepest possible level. It's not an accident or an arbitrary rule. It's a consequence of how cause and effect work, how information propagates, how the universe maintains logical consistency. Every attempt to find a loophole, every proposed method of faster-than-light travel or communication, runs into either impossible energy requirements, the need for exotic physics that probably doesn't exist, or violations of causality that would make the universe logically inconsistent. But here's something beautiful to consider. This limitation isn't really a limitation at all. It's a feature of the universe that makes existence possible. If there were no cosmic speed limit, if information could travel infinitely fast, the entire universe would be causally connected at every instant. There would be no separation between events, no possibility for different regions to evolve independently, no room for diversity or complexity to develop. The cosmic speed limit creates what physicists call causal structure, the pattern of which events can influence which other events. This structure is essential for everything we experience. It's what makes it possible for the past to be fixed and the future to be open. It's what allows for free will, choice, and genuine novelty in the universe. Without the speed limit, the entire history of the universe would be predetermined, with every event instantly influencing every other event throughout all of space and time. The richness and complexity we see around us depends on regions being able to evolve somewhat independently, developing their own characteristics before interacting with other regions. The cosmic speed limit is what creates the possibility of this diversity. Consider life itself. Life requires chemical reactions, the breaking and forming of molecular bonds. These processes take time because electrons and atoms must move and interact. If information could travel infinitely fast, chemical reactions would happen instantaneously or not at all. There would be no time for the complex dance of molecular interactions that makes biology possible. The speed of light determines how fast electromagnetic forces can propagate, which in turn determines the timescales of chemistry and biology. Our thoughts depend on electrical signals traveling through neurons at speeds far below light speed, typically around 200 miles per hour. If nerve signals traveled at light speed, our brains would be fundamentally different. The complex feedback loops and time-delayed interactions that create consciousness might not be possible. The cosmic speed limit shapes not just the universe's large-scale structure, but the very possibility of thinking. Beings like us. The universe is 13.8 billion years old according to measurements from the Planck satellite and other cosmological observations. In that time, light has traveled 13.8 billion light-years, creating an observable universe with a radius of about 46 billion light-years when you account for expansion. This finite age and the cosmic speed limit mean that we can only see a portion of the total universe. There's almost certainly more universe beyond our cosmic horizon, forever hidden from our view not because it's too far away, but because light from it hasn't had time to reach us yet. This creates a kind of cosmic humility. We're confined not just by the speed limit, but by the finite age of the universe. We can never know the full extent of reality. Some regions of space will always be in our elsewhere, causally disconnected from us, existing but forever unobservable and unreachable. But this limitation also makes the universe interesting. If we could instantly know everything about every part of the universe, there would be nothing left to discover. The cosmic speed limit ensures that the universe remains mysterious, that there are always new horizons to explore, new discoveries to make. Modern physics has revealed that the speed of light is intimately connected to other fundamental constants of nature. The permittivity and permeability of free space, constants that determine how electric and magnetic fields behave in a vacuum, are directly related to light speed through Maxwell's equations. When James Clerk Maxwell first unified electricity and magnetism in the 1860s, his equations predicted the existence of electromagnetic waves that would travel at a specific speed determined by these constants. When he calculated this speed, it matched the measured speed of light. This revealed that light is an electromagnetic wave, and that the speed of light is fundamentally about how electromagnetic forces propagate. In quantum field theory, the speed of light plays an even more fundamental role. Every fundamental force has an associated carrier particle, photons for electromagnetism, gluons for the strong nuclear force, W and Z bosons for the weak nuclear force, and hypothetically gravitons for gravity. All these force carriers travel at light speed if they have no mass, or slower if they do have mass. The speed of light is really the speed at which forces can propagate, the rate at which one particle can influence another. The discovery of gravitational waves by LIGO in 2015 provided spectacular confirmation of this. When two black holes merged about 1.3 billion light-years away, they created ripples in spacetime itself that spread outward at exactly the speed of light. These gravitational waves were detected by LIGO's incredibly sensitive interferometers. In 2017, LIGO and Virgo detected gravitational waves from merging neutron stars, and within seconds, telescopes around the world detected the light from the same event. The gravitational waves and light traveled 130 million light-years and arrived within seconds of each other, confirming that gravity propagates at the same cosmic speed limit as light. This is exactly what general relativity predicts, but it's remarkable to see it confirmed so directly. The cosmic speed limit applies not just to matter and electromagnetic radiation, but to spacetime itself. Some physicists have speculated about whether the speed of light might have been different in the early universe. Variable speed of light theories have been proposed to solve certain cosmological puzzles, but observations of distant quasars, whose light has been traveling for billions of years, show the same physical constants and the same light speed as we measure today. The fine structure constant, a dimensionless number that depends on light speed and other fundamental constants, appears to have remained unchanged over cosmic history. The universe seems to have been using the same rulebook for its entire existence. This consistency across time and space is one of the most remarkable features of our universe. The same laws of physics apply everywhere and everywhen. The cosmic speed limit that binds us today is the same limit that governed the first moments after the Big Bang and will govern the universe's far future. In a sense, by understanding why nothing can go faster than light, we've discovered something profound about the nature of existence itself. The universe isn't just a collection of stuff moving around in empty space. It's a unified four-dimensional structure of spacetime with its own inherent geometry and rules. The cosmic speed limit is part of that geometry, as fundamental as the fact that parallel lines don't meet or that the angles of a triangle sum to 180 degrees in flat space. When we push against this limit, when we try to accelerate particles to higher and higher speeds, we're not just fighting against insufficient technology or inadequate energy sources. We're pushing against the structure of reality itself. The universe is telling us through the mathematics of relativity and the results of countless experiments that this is how things are, this is how they must be for existence to make sense. And there's something beautiful about that. We live in a universe that's knowable, that follows consistent rules, that rewards our attempts to understand it with deep insights into its nature. The cosmic speed limit isn't an arbitrary restriction imposed by some cosmic traffic cop. It's a feature of spacetime that emerges from the requirement that the universe be logically consistent, that cause precede effect, that information have meaning. It connects the largest scales of the cosmos to the smallest quantum fluctuations. It links space and time into a unified whole. It makes possible the complex structures and processes that give rise to stars, planets, life, and consciousness. Without the cosmic speed limit, there would be no US to ask why it exists. The universe would be a very different place, if it could exist at all. Some versions of the multiverse hypothesis suggest that different universes might have different values for fundamental constants, including the speed of light. In those universes, if they exist, reality might work very differently. But in our universe, the one we inhabit and can study, the cosmic speed limit is what it is. Approximately 299,792,458 meters per second in a vacuum. This isn't just the speed of light, it's the speed of causality, the maximum rate at which cause and effect can propagate. It's the conversion factor between space and time. It's the fundamental constant that governs how electromagnetic and gravitational forces propagate. It's woven into every equation of modern physics, from quantum mechanics to cosmology. As you go about your life after reading this, remember that you're always moving through space-time at exactly this speed. When you're sitting still, you're moving through time at light speed. When you move through space, some of that motion through time gets redirected into motion through space, slowing your clock relative to those who remain stationary. You're not outside the laws of physics. You are the laws of physics in action, a complex pattern of matter and energy moving through the four-dimensional landscape of space-time. The light entering your eyes right now allowing you to see these words traveled at exactly the cosmic speed limit. The electromagnetic signals in your brain that allow you to think and understand propagate according to the same fundamental constant. You are made of atoms held together by electromagnetic forces that operate at light speed. Every moment of your existence is shaped by this cosmic speed limit. The universe has revealed its deepest secret to us, that space and time are united, that there is a maximum speed for causality, that this speed creates the very structure that makes existence possible. We can never exceed this limit, but we don't need to. The universe we can access, the portion within our cosmic horizon, is vast beyond imagination. Our own galaxy alone contains 400 billion stars, most with planets, many potentially harboring life. Even traveling at a tiny fraction of light speed, we could explore worlds beyond counting, make discoveries that would take thousands of years to catalog, witness cosmic phenomena that would fill libraries with wonder. The cosmic speed limit doesn't imprison us. It defines the arena in which existence unfolds. It creates the conditions for the universe to be diverse, complex, and ultimately comprehensible. It connects you to every photon that's ever traveled from a distant star, every gravitational wave that's passed through your body, every quantum interaction that's built the world around you. So the next time someone asks why nothing can go faster than light, you'll know the answer isn't about light at all. It's about the fundamental structure of space-time, the preservation of causality, the logical consistency of cause and effect. It's about a universe that makes sense, that follows rules, that allows for the existence of complex structures like stars and planets and living things and conscious minds capable of asking why. The cosmic speed limit is the speed at which reality itself operates, and that makes it not a limitation, but a gift. It's what makes you possible, what makes this moment possible, what makes the entire rich tapestry of existence possible. And that's not something to overcome or circumvent. It's something to marvel at, to appreciate, and to understand as deeply as we can. We are children of this universe, shaped by its laws, exploring its mysteries, and in doing so, coming to understand ourselves. Thank you for joining me on this journey through one of physics' most profound truths. If you enjoyed exploring why the cosmic speed limit exists and what it means for the nature of reality, please hit that subscribe button and give this video a thumbs up. Your support helps me continue creating content that explores the deepest mysteries of our universe. And I'm sure you're going to love this other video about what would happen if you could travel at light speed, where we explore the mind-bending effects of time dilation. length contraction, and relativistic journeys through space. The link is in the description and on your screen. See you there.